this video, we're going to cover several theorems which allow us to calculate the lengths of various types of segments within a circle. We're going to start with chords. If I have two chords which intersect within a circle, chords like A, B, and C, D in my diagram, then the product of the measures of the segments of one chord is equal to the product of the measures of the segments of another. And that's a really wordy definition for describing a simple idea. What it's basically saying is that if I look at my two chords as two separate parts, segment AE and segment EB make up chord AB, and segment CE and ED make up chord CD, then the product of AE times EB is equivalent to the product of CE times ED. So it's the two parts of the chords multiplied together are equivalent. So in the context of an example, such as this one, here I have CE is 12, that's this segment, it's 12. I have ED is 2, ED, this segment, 2, and I have AE is 3. I'm trying to find the length of segment EB, so I'll call that X. Well, my theorem tells me that the product of the two segments which make up chord AB, which is 3 and X, will be equivalent to the product of the two segments which make up chord CD, which is 2 and 12. Okay. When I divide by 3 to solve for X, I end up with X is equal to 24, 2 times 12, divided by 3, which is 8. So the length of segment EB is 8. Here's another example of using this idea. In this circle, I have chords PQ and RS which intersect at the point T. If PT equals 2, TQ equals 10, and SR equals 9, I want to find the length of segment ST and TR. Well, I have my segment parts already labeled. I'm trying to find ST and TR. So I'm going to label ST X. Well then TR, which makes up the rest of this chord, which has length 9, would have to be that entire chord's length minus the amount I've already accounted for in segment ST. So I end up with the product of those two segments, RT and TS, which is X and 9 minus X, will be equal to the product of the two segments which make up chord PQ, which are 2 and 10. So when I multiply those, I end up with 9x minus x squared, after distributing my value for x, is equal to 20. I notice this is a quadratic equation, so I'm going to rewrite it in standard form by bringing everything to the right-hand side. I end up with 0 equals x squared minus 9x plus 20, which I can factor. So I get a 0 is equal to x minus 5 times x minus 4. Using the zero product property, I know that one of these two factors must be equal to 0. So either x minus 5 is 0, which happens when x is 5, or x minus 4 equals 0, which happens when x is equal to 4. So then when ST equals 5, I get segment TR, which is 9 minus that 5, is 4. And ST could also be 4. And when ST is 4, I get that TR, which again is 9 minus that 4, is 5. So I actually have two distinct solutions for this question. Another theorem that we can use to help us get segment lengths is that the diameter, which is perpendicular to a chord, actually bisects that chord and its arcs. So what that means is, in the context of this example, since this diameter, I know it's a diameter because it's a chord which passes through the center, is perpendicular to the chord, it must bisect that chord, meaning that they're congruent. Therefore, x would have to be equal to 8. This theorem can also be applied to arc lengths. Whenever I have a chord and a diameter bisecting that, the length of this arc, say it was 30 degrees, would have to be equivalent to the other arc cut by the diameter and the chord. So they would also have to be congruent to each other. In the context of this example, say I have circle O with AB is 24 and OE is 5. Well, let me draw those lengths in. Here's OE is 5, and segment AB is 24. Well, since this is a diameter, which is perpendicular to the chord, it bisects that chord, and that entire length of 24 will be distributed into 2 even halves of length 12. So it will be 12 and 12. And I'm looking for the radius. Now, there are 2 radii already in this circle, radii OC and OD, but I'm going to draw in a new radius that's going to be a little bit easier to find. Recall that a radius is any distance from the center to a point on the circle. So I'm going to draw a radius OB and call that x. Well, notice that since this is a right triangle, I can use the Pythagorean theorem and I'll get my length x and I'll know what my radius is. So I end up with 5 squared plus 12 squared equals x squared, which is 25 plus 144 equals x squared, or 169 is x squared, so x has to be 13. So the radius of this circle will be 13. The last theorem we're going to talk about in this video is that in a circle, congruent chords are equidistant from the center, meaning they are the exact same distance from the center of the circle. So if I had a center for this circle O, I measure distance with a perpendicular line. So this distance, say it's 3 inches, would be equivalent to the distance to a chord congruent to this chord. So congruent chords are equidistant from the center. In the context of my example below, since I have a chord of length 6 and a chord of length 6 that makes them congruent, since I know the distance that this chord is from the center is 4, the value for x, the other distance from the center, must also be 4. Okay. There are a few questions remaining in your packet I would like you to try using these theorems, and we will discuss them further in class tomorrow.